Hi, my name is Hugo. I'm here to present our work about software deployment on heterogeneous platforms. This work has been conducted at Chalmers University of Technology in Sweden by myself, Jan Schroeder, and Ivica Crnkovic. Let's jump right into it. In the context of this work, heterogeneous platforms refer to hardware platforms containing more than one type of processor, such as CPU and GPU or CPU and FPGA. There has been a shift in industry to use this technology, which allows for higher levels of performance in computer systems, basically faster execution time and/or lower energy consumption. However, these architectures are inherently different, requiring changes in the process of engineering software in order to have it running and utilizing all capabilities of the hardware. In addition to the difference in numbers of cores, other aspects like memory management must be explicitly handled by the programmer. Furthermore, software deployment is a key aspect due to the need for allocation and mapping of software components onto the different processors that are available. So the main research question of this work is, what is the state of the art of software deployment on heterogeneous platforms? We wanted to obtain an overview of the area by focusing on two main perspectives, concerns and approaches. Through RQ1, we discovered the aspects of interest when software is deployed on heterogeneous platforms, as well as the issues that typically arise in the process. Through RQ2, we discovered the general and recurring approaches for deploying software on heterogeneous platforms. In order to answer the research questions, we conducted a systematic mapping study, which typically aims at obtaining a broader picture of the research area when compared to classic systematic literature reviews. This method includes multi-step screening process on studies retrieved from different sources, based on a set of predefined inclusion and exclusion criteria. In our case, the screening resulted in a set of 146 primary studies that were summarized and categorized to answer the research questions. The results also include other aspects in addition to the research questions, such as the main purpose of the studies, type of research, and type of validation that was used. In the figure, we see that the majority of the hardware platforms reported in the studies contained a combination of CPU and GPU. Several concerns were found, mainly related to scheduling of tasks, software quality, and software architecture. In scheduling, there were several discussions on load balancing, issues in scheduling tasks, kernels, and whole applications, including the problem of proper resource utilization. In software quality, some quality attributes were discussed as challenges when deploying software on heterogeneous platforms, including performance, portability, and efficiency. In software architecture, the discussions were around the issue of efficiently managing data and memory, given that the memory spaces are often separated and the data format across the different processing units is not homogeneous. There were also discussions on the development process, focusing on difficulties in achieving efficiency in the process and the complexity of parallel programming. Hardware was also widely discussed, even though we focused on software engineering aspects. The authors highlighted the attempts of reducing energy consumption, as well as issues related to design and maintenance. Some studies discussed the importance of evaluating the overall system through performance analysis and methods to visualize the behavior of heterogeneous systems. Finally, there were a few studies discussing the challenges of simulating such systems in order to predict their behavior. The approaches we found were separated into design time practices, runtime practices, and general practices, which are orthogonal to binding time. Under general practices, we found several approaches discussing development frameworks like OpenCL, CUDA, and OpenNP. Several studies proposed novel load balancing techniques based on aspects such as performance of the processor, aspect-oriented techniques, and bandwidth constraints. Also, some known algorithms in computer science were reportedly used in the context of scheduling, such as the greedy algorithm and earliest deadline first. When it comes to design time practices, we found some techniques to model software and hardware, such as performance models and hierarchical task graphs. The latter is also used to define software-hardware configurations, exploiting the characteristics of each target hardware architecture. Finally, when it comes to the runtime practices, we found several studies describing the implementation of their own scheduler, with different priorities depending on the context. Profiling and task queuing using either global or local queues were also reportedly used in some studies. As shown previously, most concerns in the field are related to the scheduling of tasks, processes, kernels, and most proposals are independent of the deployment binding time. The vast majority of studies propose solutions to problems rather than evaluating or validating them, which indicates a certain immaturity of the field of research, despite the fact that the concept has been around for a few decades. There is a clear lack of tool validation in practice, as well as holistic approaches to software engineering that cover refactoring for execution on heterogeneous platforms, which we are particularly focusing on at the moment. That's it for today. If there are any inquiries, don't hesitate to contact us via email. Thank you for watching.